Good afternoon, everyone. My name is Ben Greenman, and I'd like to tell you about Gradual Soundness, Lessons from Static Python. So this talk is based on a paper written by three folks from Brown University. That's Kwang Chen, myself, and Sriram, and three people from the Static Python team at Instagram, Carl, Dino, and Ani. So the paper is joint between the two of us, but the language, Static Python, all the credit for that goes to the three Instagram folks and their team members. So with that, let's get started. Oh, and this paper and talk both appeared at Programming earlier this year. So Static Python is a programming language based on Python with a few enhancements that we'll get to, and it's been running in production at Instagram for the past 2 years. And our focus on Static Python is that it's gradually typed for a very interesting version of Gradual. But first, let's step back and talk about what is gradual typing more generally. So the high-level idea is to combine the best parts of static typing and dynamic typing into a single programming language. Python is dynamically typed, so you can wind up with code like this. Here's a function called join, and it takes in several arguments. And as a programmer trying to figure out how to call the join function or how to debug it, the lack of type information can make this tough. So here our programmer is sad. There's so many parameters to this join function, and there's no documentation, and there's no type information to say what sorts of values are expected for each one of these. So in a gradually typed version of Python, we can sprinkle in some type annotations like these for data frame, Boolean, or a union of left and right. And now on the right, we have Python with types. It's the same signature as before for the join function, augmented with type info for each of these 4 inputs. And we also have a type describing the result, saying the join returns a data frame if we give it reasonable inputs. And our programmer now is happy because he or she can go ahead and maintain the function and has some starting point idea about what it's going to do based on those types. And critically, the code on the right has types in only part of it, and the rest of it is the Python that was there before. So that's where Gradual comes in with gradual typing. The whole code base doesn't need to have these type annotations all at once. They can be added piece by piece where they're most needed. So far, so good. But the real question in this space is what is supposed to happen in a mixed code base? When part of the program is statically typed and the other part is untyped or dynamically typed, what should happen when values cross between these two worlds? And in particular, these types that we've written down are compile time claims about what the code is going to do. But if untyped code is allowed to send in any value, that could invalidate those claims. That would mean those types are unsound. So what is our gradual language going to do? Is it going to make sure that the types are sound or not, or something in between? Well, there's a big design space here, and there's lots of different compelling answers. Let's focus on 3 of those possible answers for what should a gradual language do right now. And they're labeled A1, A2, A3. So the first possible answer, and this is a very popular choice, let's do nothing. Our types are going to be totally unsound. We'll use them only for ahead of time static checking, and we'll do nothing when untyped values come in. And this is the approach taken by TypeScript, MyPy, several other languages. And it's a compelling choice because you get all the IDE tools that static types have to offer. You have no performance cost from enforcing these types. So your code runs exactly like Python or JavaScript did in the beginning. The challenge here, though, is if something goes wrong and untyped code sends in a bad value to our typed function, those types are no hint about how to go about debugging the error. So your runtime semantics is just plain Python. Your debugging situation is also plain Python. The types don't help at all for that. Answer number 2 is to say, yes, let's make these types completely sound, and let's do so by enforcing them with contracts at runtime. This is what typed racket does. And now the types are a big help when it comes to debugging because they can point to a first mismatch between these typed and untyped sides of the world. But the issue here now is performance. If we're joining 2 large data frames, we might pay a huge cost for soundness on these. And that cost is going to be there whether or not there's an error. Reducing this cost has been the subject of research, lots of research for the past decade now, and it's still a tough question. So here comes answer 3, which is what static Python is doing. We've got some mix of two things called progressive static types and tags. And so we'll go more into that later in this talk. But first, I want to say it's been a successful approach so far. So I said at the start, this has been running for the past 2 years in Instagram. It's the Instagram web server, which is deploying static Python. The way it's deployed has been in a greedy ad hoc kind of way, which is very exciting. So the web server code base started off with a bunch of modules. I don't know how many, but it's well over 500. And almost all of these had optional type annotations from Pyre written in. The static Python team has been looking at what are the most expensive modules in terms of what's the running time cost of these, and piece by piece upgrading these modules to have sound types using static Python. So as of, I believe this is as of the end of 2021, double check in the paper. At the end of 21, or whatever the date is in the paper, at least 500 modules had been converted to static Python using sound types. And these were just the expensive modules. So that means there's lots of boundaries between the type and non-type world inside the code base. In fact, there's over 30,000 identifiers that cross between the different worlds. So that means there's well over 30,000 values cross between, because one identifier could carry several interactions. But this is just a coarse-grained way of saying there's a big mix of sound and unsound inside the web server, and there's lots of values going across between these worlds. There is a price to pay for these interactions, but it's offset by optimizations. And it's so much offset, in fact, that by deploying static Python on those 500 plus modules, Instagram saw a 3.9% increase in overall CPU efficiency. That is a big boost in performance. Let me unpack where that 3.9 number comes from. So the way it works is the web server is at all times serving a bunch of requests from a bunch of machines. To figure out what's the increase, the team splits these machines, or makes 2 chunks from the whole set of machines. So the chunks may not partition the entire server farm, but they're 2 significant pieces of it. So one group is our control group. They're going to be running the old version of the web server software. And the second group is the experimental group, and they're running the version that has static Python mixed in. So now we start diverting incoming requests to one of the 2 groups, and we keep sending the groups more and more requests until they've got as much as they can handle without falling over. So the control group will be running at maximum load, and the experimental group will also be running at maximum load. And the question is, how many requests per second are these 2 groups handling? And the result of this experiment was that the right-hand group, experimental with static Python, was going 3.9% faster requests per second. So that's pretty exciting at Instagram scale. How did they do it? What makes static Python so fast? Well, the first ingredient is that static Python is built on top of a separate project, improving Python as a baseline. So this is called Cinder. It was a fork of Python 3.8, I believe, at the time of the paper. Currently, it's Python 3.10. By the way, they've got advanced runtime for Python. The 2 ingredients I want to talk about are, first, there are vtables to speed up object access, and there's also a method at a time JIT compiler inside Cinder. And the JIT especially builds on extended bytecode that's been added with Cinder. So on top of the Python instructions like call function, Cinder also has some type optimized bytecodes. Here's 2 examples. Invoke method gives you a direct vtable lookup instead of the Python dynamic dispatch for function calls. And invoke function is a direct jump to a function. So we've got these bytecodes sitting inside Cinder, and that gives static Python a target to aim at, so it can produce more efficient code than it would if Python was the target. Step 1 is that we've got fast static checks happening. runtime checks for soundness. For example, if we have this untyped interaction shown here, where there's a typed function called average, which is taking in something called a checklist of ints. This means there's a list where the elements are all integers inside. And we call this typed function from the untyped world with some value called nums. This is one of those untyped typed interactions. And because static Python is sound, it needs to have a runtime check to protect it. But the check that happens is simply a tag check. So there's this constant time operation that happens asking, is this value nums an instance of this object called checklist? And this happens very quickly. It's not traversing the data structure, and it's not making some kind of proxy like you see in the contract world. So the benefit of this is that it's very fast. There is a downside, though, which says our typed average function cannot accept a built-in Python list. So even if nums happens to be a list that contains numbers, it's going to be rejected straight out because it's not an instance of this typed data structure. If we want to call average from the untyped world, we need to use the special constructor shown at the bottom right, wrapping it in checklist int. So we have faster soundness checks, but we do have a price of expressiveness when we're dealing with this type. But there's a workaround, and that is that static Python has this multi-level partitioned type system to balance between expressiveness and performance, and soundness as well. So there's 3 levels. Checklist int sits at this bottom left level. Sitting above checklist int, there's this raw type list. That's in the yellow level here. And list says nothing about the elements inside of it, whereas checklist does. So list is this coarse-grained, surface level, skin deep type, and checklist talks about what's inside the data structure as well. This top level, the yellow level with list, we call the shallow types. And these generally are talking about different kinds of values that you can find in Python, and it's only at that coarse-grained level. So hence the name shallow. And we see things like string, bool, and int, where the type is actually a pretty good description of the value, and others like list and dict, where the type is missing out what's inside the value. The concrete types give us sound data structures. So we have checklist, checkdict, and more generally, these can take in any kind of types as the element type. Now, the third level on the bottom right is primitive types, and these correspond directly to C values as opposed to boxed Python values. So whereas a Python int is a boxed object, int64 in static Python is just a number. And there's also one data structure over in the primitive world, and that is array, and that corresponds to a C array. So this multi-level type system goes progressively from weak statements and easy to use down to fine-grained statements about what's going on in the program, but harder to use. And we'll see more about harder in a second. And that expressiveness, hard to use, goes hand in hand with some limitations that static Python has on the dynamic type. So normally, if you look in the literature on gradual typing, the vision is to have a special type mixed in called dynamic, and untyped code is exactly equal to Dyn type code. So our type system has this amazing flexibility where we can mix in this type dynamic, sometimes called any, sometimes called star. And now wherever you're using type dynamic, you have all the freedom of writing untyped code. And these two are supposed to seamlessly interact and have smooth migrations from one to the other. That is not exactly what static Python is doing. The migrations are less smooth, and in fact, untyped code is different than dynamic typed code. Let me say that one more time. In static Python, you can talk to a Python module, and that's plain untyped code. You can also have a static Python module, and inside that module, you have 2 choices. You can have some types for all your variables and functions, and you could leave some of them unannotated. The unannotated ones are what I'm calling Dyn typed code, and they're held to higher standards than plain untyped Python would be. And then, of course, the type parts of your static Python code are held to an even higher standard. They're type checked. So why is static Python different from the gradual typing theory here? Because the main goal is to have these types drive optimizations. So it's less important that we have smooth migration from dynamic static Python to typed static Python. It's more important that once we've started to opt in to having types and our module is a static Python module, that we make the most out of the type information that is in the module. And so if the type system needs to nudge the developer to add in a few more annotations to make it run faster as opposed to having some foot gun sitting in there, that's exactly what the type system is going to do. And it manifests in several ways. Let me give you 3 examples of how restriction on the dynamic type helps power an optimization. So first, just sitting in the shallow typed portion of static Python, if we've got 2 typed classes and one class A gets extended by another class B, then the class B subclass cannot remove type information that was inside of the parent. Here, the parent says that f returns an int, and the child b says nothing about the return type. This is a static type error. So static Python will not allow this use of type dynamic. You've got to have at least int or a more precise type sitting there. And this helps optimize dispatch. The reason is if static Python is invoking a method on a typed class, it knows the type that that type method is going to return. And it doesn't matter if it's a superclass or a subclass instance, it knows the type. Second example, primitive types are incompatible with dynamic. If you've declared x as an int64, you cannot assign the value of x to a dynamic typed variable. Normally, every type would be compatible with dynamic type. The primitives are not compatible because there would have to be some kind of conversion sitting there. So this is helping you as the programmer see, all right, I've got these C values here. Let me make the most of them, and let me make sure that they get sent only to compatible C value operations. Third example, concrete enables fast checks at the boundary. So similar to what we saw before, where there was an average function expecting a checklist and it was incompatible with Python list. Here we have an average function that's expecting a checklist of dynamic, and it's being called with a checklist of int. These two are incompatible. This is a runtime error because checklist dynamic is a different constructor than checklist of int. If it was a compatible constructor, we would need more complicated checks at runtime. And we'd also need to sprinkle checks throughout the body of the average function whenever we pulled the value out and wanted to use it at a specific type. So this way we have restrictive boundaries, but a lower cost to pay each time we cross them. So that's step 3. That's a sense of the limitations that the dynamic type has and how they enable optimization. And then finally, static Python takes a limited scope. It is not the final type system for the Python world. Again, the focus is on what types drive optimizations. The focus is not on having a complete type system that covers every corner. So in particular, some behaviors do not get predictions from the type system. If you use things like multiple inheritance, the behavior is exactly the Python behavior, and the type system does not make any claims about what's going to happen. Second, if you're using types that static Python doesn't have full support for yet, and these include callable, set, unions with multiple things, these all can get deferred to the Pyre optional type system. So static Python will give you optimizations and precise checks for a subset of the types in your program. Pyre will give you some static only checks for a greater number of types. And then Python covers the full behavior that your program will have, whether or not any of these type systems can reason about it. So these are the key steps to how did static Python get so fast? And the main one, especially from research perspective, is that it's got this progressive type system that lets you balance hard to use types that give you the most performance and easier to use types to help you first make that initial migration from untyped Python or from Pyre annotated Python over to the static Python world. And let me back that up with a bit more experience centering on these progressive types. So here's a more recent update. Instagram, as of March 23, has now over 900 modules using static Python types. 10 of these modules are using the concrete types. 16 are using the primitive types, and the rest are all using shallow types alone. And performance is still good, slightly better than before. I don't have the exact number for what the web server is doing, but if a conversion to static Python didn't improve performance or keep it the same, then the conversion wouldn't go through. It would be modified to have more primitives or more concretes. So all these 959 type modules are a success. What I do have in terms of performance numbers is data from 4 micro benchmarks. So these bars here are all relative to Python, and a lower bar is faster performance. So there's 3 bars. The first bar is exactly the Python bar. The second bar is what happens if we use only shallow types in the benchmarks and do a quick light touch conversion. Then the third bar says what happens if we mix in concrete and primitives and really try to get performance out of these types. So for half the micro benchmarks, the yellow shallow bar is lower than the Python bar. So that's excellent. With very little effort, you get a performance improvement on Delta Blue and on Richards. For the other 2, Fankuch and N-Body, they're slightly slower with shallow only. And that makes sense for those micro benchmarks because they're doing a lot of number crunching. But when you mix in primitives, so now those numeric operations get unboxed and much faster, now we're well below the 1x line from Python. So sometimes you get good performance out of the box with shallow, and if not, it's well in reach for these micro benchmarks using concrete primitive. Now let me wrap up. First, I have 2 comments for researchers in the gradual typing space. One is we could use more information about what is the guaranteed performance trade-off for different aspects of gradual typing theory. So in particular, when we talk about the restrictions that static Python has on the dynamic type, it's breaking the gradual guarantees, and it's breaking them in specific places because it needs to get a performance boost. So it's worthwhile separating what is the payoff of a theoretical property like the gradual guarantee and what is the cost of it in terms of what sorts of optimizations do we lose, broken down by different types and different language features. So in the static Python case, I'm thinking about what's the cost of having this guarantee for classes and subclasses. And the cost is in terms of optimizations on dispatch, and now you suddenly cannot have dynamic on your subclass. So breaking these things down by language features, showing what's gained and lost, could help other language designers find the best point for them in this complex design space. Second, I want to point out this concrete types as a good space for further research. There's 2 notable prior works here, the Thorn language and the Nom language, and several others, Safe TypeScript and StrongScript. We could use more research here. So for example, what's the best way to migrate a shallow type like list up to the checklist world? Right now, you might have to modify any arbitrary part of your program. Once you've added a checklist, every value that goes into that annotation needs to be upgraded. So as the programmer, how do you find those? There's space for research tools that could help with that. And then second, I mentioned briefly that static Python does not have support for union types with multiple alternatives. So 3 or more things, that's not implemented unless they happen to be, one of them is false and the other 2 are equal. And the reason that's not there is there's no constant time check for a union with multiple alternatives. So how can we make that sort of check as fast as possible? Other things to make concrete as efficient as it can be. Takeaway category number 2 for practitioners coming from Ruby, Clojure, maybe PHP, JavaScript. This mix of shallow and concrete types and gradual soundness is a promising one. So why not your language? Try to implement it and let's see if we can replicate the static typing story in another domain. And then a third comment for language designers more generally. In the paper, we talk about how we created a Redux model for static Python. And this was a very high payoff activity at a relatively low cost for us. So we were able to find 5 critical soundness bugs in static Python and 16 other correctness issues. All of these have been fixed by now, but for the low cost of creating the Redux model, we quickly found lots of important bugs, and this was in a language that had been running in production for well over a year at that point. So it's a great advert in favor of Redux. Go Redux. Now with that, I will wrap up. So I'll post a link to the paper down below in the bucket, and I'll also post a link to the static Python repo so that you can explore the code base and check it out. So thanks for listening. Have a great day.